Welcome everybody to the ASF NISAR Community Workshop 2, Mapping Change with SAR Imagery. So these workshops are intended as skill building resources wherein we review concepts and workflows that will be applicable to working with NISAR data when they become available next year. And so with me today from the Alaska Satellite Facility are Heidi Christensen, Jacqueline Smale, Dr. Forrest Williams, Dylan Palmieri, and Sergeant Shriver. And so whoever is not currently speaking is available to take questions in the QA. So please, if you have questions, post them in the QA. You can also post them in the chat, but they're probably easier to manage and find in the QA. And also we would like to extend our deep thanks and gratitude to Dr. Y.S. Rao from the Center of Studies and Resources Engineering for his efforts in organizing and informing all of the participants in this in these workshops. Next couple slides, please, Heidi. All right, and so before I get into the agenda, I just want to point out that we will be presenting from this slideshow that you're seeing on the screen now, and these slides are available for everybody to look at and review on your own. So you can scan that QR code, and if somebody else could pop the link to this slide deck into the chat, that would be great. Thanks, Heidi. Yep. So the link to the slide deck is slideshow is in the chat, and this is you know, the access is set so that everybody can view the slideshow without a password or anything. And could you click on to the next slide, Heidi? All right. So so this is a 2-day workshop, and so on day one, we'll start with this introduction that I'm presenting right now, and then Heidi Christensen will pick up with an introduction to SAR, and then I'll follow that with an introduction to our web service Vertex for data discovery and download. Then we'll take a break, and then after the break, I'll give a small introduction into radiometric terrain correction (RTC) and using HyP. Then we'll wrap up with a short QA session, but mostly we'll be focused on making sure that everybody has the access that they need to Open Science Lab and Open SAR Lab, and that they've cloned in the repository containing the notebooks that we'll be running tomorrow, and built a conda environment from that repository. And so that's how we'll spend our final hour today. Just a note that much of the early material, the introduction to SAR and the introduction to Vertex, are much the same as we presented during the previous workshop. So if you attended the previous workshop, some of this early information may be a repeat. It never hurts to hear it more than once. But if you're comfortable with that material, you could also step away until you know, later in the day when we go over newer material such as RTC and setting up your environments for tomorrow. Then on tomorrow, on day 2, we'll start with an introduction to interpreting SAR delivered by Jacqueline Smale, and then Forrest Williams will present an RTC-based landslide detection theory, and then we'll take a break, and then everybody will have the opportunity to walk through a notebook that actually performs some RTC-based landslide detection. And then we'll conclude with a final wrap-up and a QA tomorrow. Next slide, please. All right, and so before we begin with Heidi's presentation, I'd just like to point out some logistical links here. So there is a slideshow of of workshop prep slides that that looks like Heidi's pasting the link to in chat. And so this walks through gaining access to OpenSAR Lab, cloning in the repository containing the notebook and the environment that we'll need, and then building the environment that it contains. I know that there was a small issue with the slideshow. If you received it over the weekend and attempted to build the environment, there was an outstanding pull request, and so you'll probably have to rebuild that environment because the environment that was there prior to yesterday morning wasn't quite up to date. But once again, we'll go over all of this preparation at the end of today, and so you'll have an opportunity, with everybody, with all of us presenters here in the room to work through those as well. So if you ran into any troubles, we'll be able to resolve those a little bit later in the day. There's also a link to the ASF data search Vertex website, and that's our web app for data discovery and download, and it also interfaces with a number of other ASF services such as HyP on-demand processing, which you can use to order the RTCs that we'll be using for this workshop, although we will be using staged and pre-prepared staged data. This service can be used to order additional RTCs for your own areas of interest for performing your own analyses. And then there's a link to Open Science Lab, and then the USO at asf.alaska.edu is our user services email. So if you have any questions after the workshop, this is the email that you can use to send those questions in, and our user services group will make sure that your questions end up with the right people to answer them. And then one more thing is at the bottom, the last link is ASF's YouTube channel, and so this is where the videos of this workshop will be hosted once they're prepared. We were, I think, during the first workshop, we said we'd have them up within a week, and it turns out that it takes a little bit longer to prepare those than we'd realized. So it will probably take a good couple weeks before those are available. But you can find the videos from the previous workshops at that YouTube channel and also on the ASF website. All right, next slide, please. All right, and now I'll hand it off to Heidi.
Thanks, Alex. I'll be presenting a very basic introduction to synthetic aperture radar. And as Alex mentioned, for those of you who were at the last workshop in August, much of the content will be the same, but I do have a little bit more time today, so I can go into a little bit more detail. SAR makes use of the microwave range of the electromagnetic spectrum. These are wavelengths that range from about 1 centimeter to about 1 meter. And that's much longer than the range that's used for optical imaging, which is generally less than a micrometer. There's a benefit of having these longer wavelengths just in terms of understanding how the signal interacts with the Earth's surface, because the wavelengths are an understandable length. Like when I think about a micrometer, that doesn't mean very much to me, but I know what a centimeter is, and I know what 25 centimeters is. And so we can really think about how those signals will interact with various objects on the Earth's surface in very real terms. Another advantage of this part of the electromagnetic spectrum is that it's very clear for the signal to pass through and image the Earth's surface. There's not a lot of atmospheric disturbance when you're creating an image from SAR data. This means that unlike optical imagery, you can be collecting an image of the Earth's surface anytime, regardless of the cloud conditions or if there's smoke present. And this makes SAR a very valuable tool for monitoring the Earth's surface during times of hurricanes or intense flooding where there is a lot of cloud cover at the same time, or if there are wildfires that have a lot of smoke. In addition, areas that are prone to frequent cloud cover, such as the rainforest, where it's difficult to monitor deforestation, for example, with optical imagery, because there are so few days when you can actually see through to the Earth's surface. But SAR can always reliably capture an image. There are atmospheric impacts. So sometimes if the conditions of the atmosphere are different from one acquisition to the next, there are delays in how long it takes to acquire that image. But in terms of the amplitude data, which is what we'll be focusing on mostly today, we can always create an image, even if there are delays. And the delays are more of a concern for NISAR, which we went over in a fair bit of detail during the last workshop. But the important thing is that we can always get an image of the Earth's surface, which is really valuable. The other important thing to note about SAR is that it creates its own illumination. So there's a very controlled signal that's sent down to the Earth, and only the returns of that very controlled signal are measured when they come back to the sensor. So it has nothing to do with the sunlight conditions. That means that we can collect an image anytime, night or day. It doesn't matter at all what the sun conditions are doing. Now, the combination of those two characteristics, being able to create its own illumination and see through clouds and smoke, makes SAR an excellent tool for monitoring surface processes. As I mentioned, this is particularly important at times when there's cloud cover or if there's smoke from wildfires. With the newer constellations, there are very regular repeat cycles. And so you get these very nice, regularly spaced intervals of acquisitions that you can rely on through time to look at changes on the Earth's surface. SAR uses an interesting way of generating an image. It's quite different from optical imagery. And one key aspect is that it's always looking down to the side. There's a side-looking geometry. So there's a pulse that's sent down to the Earth's surface, and the way that it measures where things are on the Earth's surface and how much of that signal is coming back from any one place on the Earth's surface is by the timing of the returns. So the near range, stuff that's closest to the sensor, will come back first, and then the far range will take longer to return. So it's mapped to the surface based on the timing of those returns. Now, if we were to have a nadir approach where we're looking straight down at the Earth's surface, which is commonly used for optical imagery, but that wouldn't work for SAR, because if you're looking down, you could be getting returns coming back from the left and the right side of the sensor at the same time, and it would be ambiguous. It would be impossible to tell which direction that was coming from. So by looking off to one side, you don't have that ambiguity. It's the closest data is from the near range, and the farthest data is from the far range, but it's all in that same direction. So that's really key for collecting SAR data, but it does mean that there are distortions that are inherent to the SAR data set because of that side-looking geometry. So the problem with using radar to image the Earth's surface from space is that resolution degrades with the distance between the target that you're measuring and the distance to the sensor. So if I wanted to use a traditional radar sensing imagery system from space, if I had a 10-meter antenna, I would be getting a resolution in my image on the Earth of about 5 kilometers. And that's not super useful for imaging. One way to get around that would be to fly a sensor that had a much longer antenna. The problem is that to get a resolution on the Earth's surface that's reasonable, such as 10 meters, I would need an antenna that's 5 kilometers long to be out in space. And it's just physically impossible to fly an antenna that's that long. So the way that we get around this is by using a synthetic aperture. And basically, SAR makes use of the motion of the sensor as a proxy or a stand-in for a long antenna. So there are acquisitions that are being taken as the sensor moves along. And at some point, there will be an object on the surface that is in many of these different acquisitions. We can use those many acquisitions and combine them together to synthesize a long antenna. So basically, this distance that it traveled stands in for having a long antenna, and we can combine those images and focus them into an output image that's very high resolution, even though we're able to fly a sensor with a reasonably sized antenna. So we just use that motion rather than an actual physically long antenna to create these high resolution images from space. And at that point, it doesn't matter how far the sensor is from the surface. You can always be generating that same resolution. There are two components of the SAR dataset, the amplitude and the phase. The amplitude is what we're going to be focusing on most today. And that is how much of the signal that's sent out actually returns to the sensor to be measured. This is often called backscatter, or it can be referred to as intensity or amplitude. The amount of backscatter is impacted by the sensor properties themselves, but also the physical and the dielectric characteristics of the scatterers on the Earth's surface. And I'll be going into much more detail on that, and we'll be talking a lot about amplitude in this workshop. But I do want to mention the phase as well, which is what we focused on more in the last workshop. And the phase is the location of the signal along its wave cycle when it returns to the sensor. And that can serve as a proxy for distance. And that's used both to focus the image, but it's also the basis of SAR interferometry. So basically, if you collect an image, you get the phase measurements, and you come around your orbit and collect another image over the same place on Earth and the same place from the same place in space. If nothing has changed on the Earth's surface, the phase measurements should be the same. If, however, the Earth has moved, so if the ground has moved either away from or towards the sensor, that will mean that the signal takes longer to get back to where it started from. So that the travel path, it goes down to the Earth's surface and goes even further than it had to the first time. So in this case, in this image, you can see that an earthquake caused some subsidence of the ground. So that signal went down to the Earth's surface, but had to go even further. And so it'll be further along in its phase when the signal comes back. So we can compare those two phase measurements from the two different acquisitions to output an interferogram. And the interferogram gives us information that allows us to identify areas that have undergone surface deformation, and also to quantify that surface deformation. So in this interferogram, you can see there are these fringe patterns, and the closer the fringes are to each other, the higher the amount of deformation took place in that area. So you can see right along the fault, there's the highest amount of deformation. And we can then apply some calculations to determine how much deformation took place. We won't be covering NISAR really at all in this workshop. That was the focus of the previous one. So if you weren't able to attend the workshop in August, we do have, as Alex mentioned, the recordings are available. So here are the links. And also, I believe I posted the link in chat to the YouTube channel. Yeah, that was the last link that I posted. They're available there, and this is where you'll also find the recordings eventually from today's workshop. So let's get back to amplitude. Backscatter is the amount of the signal that's sent out from the sensor that actually returns to the sensor to be measured. And radar images are formed by processing all of these backscatter measurements from the acquisition to create an actual image that shows you where the backscatter is coming from on the Earth's surface. So it maps those returns to the Earth's surface. There are a number of different ways that the signal can interact with the Earth's surface. We have one of the simplest, which is specular reflection. And this is when you have a flat surface, you have a signal that's coming in on an oblique angle, it hits that surface and bounces off, but it bounces off in the completely opposite direction of where it came from. So very little, if any, of that signal actually is sent back towards the sensor to be measured. On the other hand, if you have a rough surface, you can get diffuse scattering, where the signal comes in and then it kind of bounces off in a number of different directions. It's still just interacting with a surface. It's one interface between the signal and the Earth's surface, but it can bounce off a number of different features before coming back to the sensor. And when you have these rougher surfaces or a number of different angles of surfaces, there's a greater chance that some of that signal will be redirected back towards the sensor. Now, volume scattering is another type of diffuse scattering that takes it to a different level of complexity. And that's when you have all kinds of planes and interfaces for the signal to interact with. So a really common volume scatterer is vegetation canopy. So if you have a forest with lots of leaves and twigs and branches and a tree trunk, there are all of these things in different orientations where the signal can kind of bounce off, and it has this complex set of interactions with this entire volume rather than just a surface before it's returned back to the sensor to be measured. And then last, there's dihedral reflection. And this is a very efficient way of getting the energy back towards the sensor. And this is when you have your horizontal surface, the signal comes down, it hits that bottom surface, but then instead of just bouncing off into nothing, it hits another object that's a vertical object. And so it hits that object, whether it be a building or a tree, and that's redirected back towards the sensor. So you have a very targeted redirection that's coming back towards the sensor. So you tend to get quite high returns from these double bounce features. And in fact, this is the concept that's used to calibrate SAR sensors. We have these dihedral corner reflectors that are angled just so that it can very efficiently harness that signal that's coming down and redirect it exactly back towards the sensor with the maximum amount of signal returning. So you would minimize the amount of loss of energy. Backscatter characteristics and the values are determined both by the sensor and the target characteristics. Now, the sensor characteristics, there are a lot of different configurations that can be used for SAR sensors. And it's important to be aware of what configuration was used to collect the data that you're looking at, especially if you're comparing one data set to another. If you're comparing data sets that were collected with different sensor configurations, you may be misled to think that there's a difference happening on the Earth's surface when really it's just a difference in the way that the image was generated. So some things to be aware of are the wavelength or the frequency of the SAR sensor and the polarization of the transmitted and received SAR signal. We'll be going quite a lot in depth into those two in future slides, but I want to mention those. And then also the incidence angle. So the radar can be set to image the Earth from a range of different angles. There's kind of an accepted range that's used, but specific sensors may be configured to take advantage of a very specific incidence angle. And the angle of that incident signal really impacts the way that it interacts with the Earth's surface and the scatterers that are there. So it's important to be aware of the incidence angle that was used for acquisitions. There may be different modes, even with the same sensor, that sort of leverage different incidence angles so that you're highlighting different aspects of the ground features. In addition, there is a range of incidence angles that occurs across an image acquisition, because there is the near range and the far range as the sensor is looking down. And so the incidence angle from the far range will be a little bit different than from the near range, even in the same image. The look direction of the sensor is also important. Many of the larger SAR sensors, or especially the spaceborne SAR instruments, are set to look in one direction only. Some can pivot around and change look directions, but many of the larger missions tend to be looking the same direction all the time. So if you have a right-looking sensor, it's looking off to its right. So if it is orbiting from south to north in its orbit cycle, it will be looking off to the east. If it comes around on its orbit pattern and it's coming down over that same patch of Earth, but from north to south, then we would expect it to be looking off to the west. Now that makes a difference, especially in areas that have high terrain. And this is particularly important for NISAR analysis, but also even when doing amplitude-based time series analysis. In areas that have really significant terrain or a lot of mountains, you can be getting really different information if you're looking at the features from one side versus the other. And in fact, there are some algorithms and some workflows that actually combine data from the two different directions. So you take the amplitude from both look directions and take the best parts of each so that you can kind of be filling in the gaps. In some cases, Alex will be talking more about the potential errors or the distortions that are in SAR images. And there are some times where you have a radar shadow where the mountain is such and that the angles are such that you can't really see some parts of the backside of the mountain. And so by combining information from different look angles, you can sometimes fill in those gaps. But at the same time, if you're just doing a time series analysis and interspersing different look directions, depending on your site, that can lead to some interesting results. So just be aware of the look direction of the acquisitions and make sure that it's appropriate. If you are combining them, make sure that it's appropriate for your particular application before you do that. So the characteristics of the targets on the Earth's surface also impact the amount of backscatter that will be returning to the sensor. Some of the key characteristics that really impact backscatter are surface roughness and vegetation structure. So if you have a rougher surface or more complex vegetation, you will generally get higher backscatter returns. Another really key component is moisture. Water has a high dielectric constant, and so when it's added to things like soil or vegetation, it increases the ability of that surface to reflect the signal. And so if you have higher soil moisture, you tend to get higher backscatter than you would if the soil is dry. Similarly with vegetation, if the vegetation is very moist, you'll get higher returns than you would get from very dry vegetation. This comes down to the dielectric properties of the scatterers that are on the Earth's surface. And the dielectric properties essentially tell you about the permittivity of an object. So if there's a material that has a high dielectric constant, that means that it's very effective at reflecting microwave waves. Whereas objects that have low dielectric properties are more able to absorb the energy from the microwaves. And so if you have something that has high dielectric properties, it's more likely to reflect the signal, and there's a higher chance that that signal will be able to return back to the sensor, whereas very low dielectric properties of an object would mean that it is able to absorb that signal, and it may absorb it so well that none of it can escape back to be returned to the sensor. I mentioned that the microwave spectrum has quite a range from 1 meter to 1 centimeter, and but there are very specific bands within that range that are commonly used for SAR, and each one of these bands that's commonly used has a different application. If you have a need for very high resolution imagery, the sensors with the lowest wavelengths will be able to provide the highest resolution. But at the same time, those small wavelength signals also have a lower ability to penetrate into vegetation or into soil. So if you're interested in dynamics that are happening further down in the canopy or on the forest floor, or similarly down deep in the soil rather than just the surface, you may want to use a a sensor with a longer wavelength. When you're thinking about NISAR, the value of a longer wavelength is that it can penetrate most vegetation. And so you're actually focused more on the crust of the surface rather than the vegetation dynamics on top. So if you want to kind of see through all that vegetation, then longer wavelengths tend to be better. But the band that you use really depends first on your application and which one is most suited to your application, but also the availability of the data. We have C-band data easily accessible from Sentinel-1. And so even in cases where it may not be ideal, it's there and it's free. So often we make use of that instead, even if an L-band sensor would be more useful. So it's a combination of what you need for your analysis and then also what's available. So the smallest wavelength that's commonly used for SAR imaging is X-band, and that has a wavelength of around 2.5 to 3.5 centimeters. Again, that gives you the opportunity to have the highest resolution image, but it can't penetrate vegetation very well. So it can be good for urban monitoring or looking at ice and snow or other things where you're looking at very sparse vegetation or features that are quite small that you want to be able to differentiate from each other. The C-band sensor is what is available on Sentinel-1, and it's often used for global mapping, change detection, and to monitor areas with low to moderate vegetation. The other common band is L-band, and that is a much longer wavelength, usually around 25 centimeters. And that has much higher potential to penetrate vegetation. So it's excellent for NISAR. It has also the ability to detect greater amounts of change in one event. So if you have an earthquake that moves the earth very far, it may not be possible to quantify the actual amount of deformation with a C-band sensor if the amount of movement is more than half of a wavelength of that sensor. So if you have a lot of movement, the longer wavelength may help you capture that amount of movement. So the X, C, and L band are kind of the most common, and the L band will be flown on the upcoming NISAR mission. But in addition to that, there's also the S-band sensor that will be flying with the L-band sensor on the NISAR satellite. That will be collecting data over India mostly, and it will have an intermediate wavelength between C and L-band. And so it's going to be really interesting to see how people use those two different bands, the S-band and the L-band, which will be collecting at the same time, and be able to compare those data sets and determine what kinds of information they can pull out of those comparisons. The P-band is a very long wavelength, and it is not commonly used for spaceborne missions. It has difficulties with some of the ionospheric interactions. The atmosphere can be problematic, but there is a new mission, Biomass, that's due to launch. It was due to launch in 2024. It's delayed because of the launch, the launch vehicle issues. But that will be a spaceborne P-band mission, which will be very interesting to have that data available. But then there are also some airborne missions that use a P-band. So again, the wavelength really determines how far the signal can penetrate into both vegetation and also soil. So if you're using X-band, you're really getting information from the top of the canopy if you're looking at a vegetated forest area. With C-band, it can penetrate further into that canopy. So you're getting more information about the canopy structure. Whereas L-band, that can often penetrate directly through the canopy and down into either the forest floor or at least the structure of the trees, the trunks and the branches. And similarly in the soil, the X-band is really telling you about the very surface characteristics, while C-band gives you a little bit more nuance in terms of the soil column. And then L-band may be getting you more information down around the root level. So these data sets are complementary. They can be used in combination to determine a range of information. But you also do have to be careful if you are comparing two data sets to make sure that they are collected using the same wavelength, because the different wavelengths do tell you different things about the Earth's surface. So here's an example of X-band versus P-band, so kind of the two ends of the spectrum. The X-band on the left, you can see that it's really just showing the top of the canopy. So I see here basically a forested area with a river. In the image on the right, we're seeing through the canopy, and actually we're able to discern building footprints and other infrastructure and some of the characteristics of the forest floor. So this area may be just dry and without much undergrowth, and so it's just able to absorb the signal very well. So very little of it comes back to the sensor. Whereas over here, we can see actual tree trunks that are reflecting that signal back towards the sensor. So we get a bit of a different view into what's going on underneath all that leafy canopy, whereas with the X-band, we're really looking at the tops of the leaves. Polarization is important and refers to the orientation of the electric field of the signal. Most radars are designed to transmit and receive in either vertical polarization or horizontal polarization. There are some sensors that are configured simply as single pole sensors, which means that they send out in one polarization and receive in one polarization, and that's it. So, for example, they might send out a horizontally polarized signal and receive a horizontally polarized signal, which would give you an HH polarization. We often talk about polarizations with two-letter codes, the send polarization and the second letter vertical returns, that would be VV. And there are some sensors that can also, that are dual pole. So it sends out in a vertical or horizontal polarization, but can receive both those same polarized, the co-polarized returns, but also the cross-polarized returns. So if I'm sending out a vertically polarized signal, I can measure the vertical returns, but also the returns that are horizontally polarized. So that would give me VV and VH. Similarly, I could send out a horizontally polarized signal and receive both the horizontal returns, but also the vertical returns, which would be HV. A Sentinel-1, for example, is a dual pole sensor, but it has the ability to change which polarization it uses as the primary polarization. So over the land, it generally collects with a primary polarization that's vertical. So you're sending out in vertical and you're receiving both vertical and horizontal. So you get the VV and the VH. But then once it gets to the oceans or the polar regions, it switches so that it sends out a signal in horizontal polarization and receives the horizontal and vertical returns, which gives you HH and HV. There are some sensors that are configured to send and receive both in vertical and horizontal polarization. So that's called a quad pole acquisition. So you have signals that are going out both in the vertical polarization and the horizontal polarization, and you're measuring the horizontal and vertical returns of both of those sent signals. So that gives you HH, HV, VH, and VV. And each one of these polarizations tells you something different about the surface characteristics. So if you do have that quad pole data, it's a very rich data set, and you can learn a lot about the Earth's surface when you do have all of those options available. There is, however, a cost of acquiring all that data. It's a lot of information, twice as much. And so the sensor has to be able to accommodate that and also downlink all that data to the Earth. And because of all those processing costs and the burden of transmitting all that data, often there is a trade-off that the quad pole imagery has a much smaller footprint. So you're getting a very high quality data set with lots of information, but it will generally have a smaller footprint. And many of the missions that do have quad pole capabilities only use that part of the time, so that they're able to do more global mapping. But then for certain areas, you might get these higher quality data sets with more information. But it does come at a cost. So the different polarizations react differently with surface scatterers. The VV polarization is particularly sensitive to surface roughness. So when you have specular reflection, you'll get very little of that VV return. But as soon as you get a little bit of roughness on the surface, you'll start seeing VV return. So if you have a lake on a calm day, it can be very low backscatter coming back. But as soon as there's a little bit of wind on the surface, for example, in northern Alaska, we have lots of lakes that are amidst tundra, and there are no trees. There's very little landscape. It's just tundra and lakes, and so you get these high winds that can just blow across, and it can be very hard to differentiate between water and the surrounding tundra, just because the roughness is about the same. So the VV is very sensitive to those surface roughness. HH is very sensitive to double bounce scattering, so that dihedral reflection, and where you have the signal coming in. For example, if it were to in an urban setting, it hits a parking lot, for example, a very smooth surface, and then bounces off a building and back to the sensor. So you get very high returns, especially in HH. Same thing on the ocean. You have a signal that's coming in, it's hitting the smooth surface of the water, but then if there's a ship there, rather than just scattering off into nowhere, it's hitting that ship and returning back to the sensor. The cross-polarized returns, either HV or VH, are very sensitive to volume scattering. So if there is a vegetation canopy, you will see the more complex the vegetation, the higher the returns will be in that cross-polarized polarization. So either HV or VH. There are other volume scatterers as well. Ice can serve as a volume scatterer, especially when there are different inclusions in the ice, either air pockets or bits of soil or rock. That can also serve as a type of volume scatterer. So just to review, we've got the specular scattering. So on a lake, you would expect, if on a calm day, you would expect very low backscatter from surface water. You have the vegetation, which has increased surface roughness, but then also is a volume scatterer. So both in VV and in VH, you would expect higher returns. And then you have a building here that's very bright. And again, that's the angles that are involved. You would expect to see very bright returns, both in the VV and the HH, where you have that specular reflection that's then hitting another thing and being reflected back towards the sensor. You can see also in urban settings where you have roofs or other infrastructure that's angled directly back at the sensor. So you can be getting some of those direct bounces as well. So it doesn't necessarily even have to be double bounce, as long as the angles are right to just send that signal directly back to the sensor. So Alex is going to go over the real technical details of radiometric terrain correction, but I'd just like to give a brief introduction. Radiometric terrain correction is really what makes most amplitude data useful in many workflows. If you look at GRD of Sentinel-1 data, this is collected over Juneau, Alaska, which has really rugged mountains. And you can see that the mountains look kind of squashed over with a bright leading edge. And that's because of the distortions that are inherent to SAR because of those side-looking acquisitions. So we have a mountain slope, and because of the angles involved, the signals coming down, it's possible for the signal that's being bounced off the top of the mountain and the bottom of the mountain to be coming back to the sensor at about the same time. So the sensor interprets that as being all from the same place on Earth, when really it's an entire mountain slope that's contributing those backscatter returns. So radiometric terrain correction, or RTC, uses a digital elevation model to adjust for these distortions. So first of all, it takes the pixels from the mountaintops and puts them over in the place that they should be if you were looking down from above rather than from an oblique angle. And it also normalizes the backscatter. So all of that information that's coming back from the slope is spread out over the actual surface area that is contributing to that backscatter return. So you have the mountainside, you calculate from the DEM the surface area that's actually contributing to that signal return, and then normalize those returns appropriately, considering the amount of surface area that's actually contributing. So once RTC is complete, you can see here in the image on the right, we now have mountains that look like they are where they should be if you're looking down from above. And the front sides and the back sides of the mountains have much more similar radiometric signatures than they did in this original image. Now, RTC is particularly important if you want to be using these data sets, a SAR data set, in conjunction with other types of data. So if I were to overlay this GRD on a map that had in situ data or some other raster data sets from optical images or the DEM, none of those things would align with the features that I'm looking at here. And so to have a meaningful interaction and be able to compare well between our SAR data and all of these other geospatially enabled data sets, we need to make sure that that data set is corrected, that we've corrected those distortions. That said, there may be applications where you don't need to apply these corrections, or that you would only want the terrain correction and not the radiometric flattening. But if in doubt, generally start with the RTC, unless there's a very compelling reason for your particular application not to do those corrections. But certainly be aware that if you were to just take a Sentinel-1 GRD and put it in a GIS, it will show up where you expect it to be, but those distortions will potentially make it very difficult to do any analysis that's comparing to other data sets until you do that radiometric terrain correction. And with that, I'm going to pass it over to Alex to give an introduction to Vertex.
Great, thanks, Heidi. So I'm just going to share my screen here. I think I can probably take over from the top of yours. Okay, are you seeing my, no, you're seeing the wrong thing here. Do you see the slide presentation or something else?
We see something else.
I see something else.
Okay, let me try this again.
Yes, yes.
Okay, is that better?
Yes, it's not in slideshow, but we can see your slide. Yeah.
Great.
Perfect.
Okay, so I'm going to present an introduction to Vertex, which is our web app for data discovery, excuse me, and data access, and it also interfaces with services such as HyP on-demand processing. Before I jump into that, I just want to give a brief introduction to ASF and explain who we are and what we do. So the Alaska Satellite Facility is a NASA DAC, which is a Distributed Active Archive Center. And so we archive and distribute SAR data. And as part of that mission, we also provide educational resources to explain how to access those data, and then how to use and analyze those data, because SAR is such a complex data set. So there are 12 DACs around the United States, and so we are in Fairbanks, right here in the interior of Alaska, and we maintain archives of SAR data from NASA, ESA, JAXA, the Canadian Space Agency, and then when NISAR comes online, I believe we will also be hosting some of the S-band data from ISRO as well. And and so, you know, our big mission here is to not only archive, but to disseminate this information in a way that is usable. And so so that's why we deliver courses and workshops such as this to explain to users of our data how you know, how they can use and interpret those data. And so the tool that we've developed to aid in the discovery of different data products and accessing those data products is Vertex. So in years past, if you wanted data, you would submit a request, and we would ship you a physical copy of that data through the mail. But now most, you know, pretty much all of our data sets are hosted in AWS and are accessible online, and so you can access them through the Vertex website. And I'll now hop over to Vertex. So you can get there with either by scanning this QR code here, or just typing in this URL into your web browser. So it's search.asf.alaska.edu. And then you'll find yourself here in Vertex. You're seeing Vertex now, right? I'm sharing the Vertex screen.
Yes.
Okay, great. Okay, and so when you land in Vertex, you know, you can search the data without having signed in. But if you wish to download or order any on-demand processing, you will need to log into the site with your Earth Data login credentials, and you'll also have to have accepted the EULA for ASF data access. And so there are instructions on how to go about setting up your Earth Data login account in that preparatory slideshow that we shared for this workshop. And then we'll also be going over that at the end of the workshop as well, of today's session of the workshop. So once you're in Vertex and you've logged in, at the moment you can select between two different languages, English and Spanish. We hope to extend these language capabilities. So at some point in the future, Hindi may appear on this list. But at the moment, we have English and Spanish, and we've just released the Spanish version of the website within the past several weeks. So there are a number of ways to search for data on Vertex. First of all, you can select the particular data set that you're interested in. So currently, the site defaults to Sentinel-1. Which is by far the data set that receives the most downloads. However, we expect that when NISAR launches and we start serving NISAR data, we'll probably replace Sentinel-1 with NISAR as the default data set to search. However, we do have a number of other data sets that you can search as well. One exciting new development, which is also part of Sentinel-1, are S1 bursts, and so so Sentinel data acquires well, most of the SLCs that you'll find on Vertex were acquired in a wide mode, and so they're comprised of three different swaths of bursts. Each of those contain somewhere in the realm of eight or nine bursts per swath, and so you get about 27 bursts approximately per Sentinel scene. And whereas the frames for a Sentinel, excuse me, a Sentinel-1 scene can shift. The path stays consistent, but where that frame is located in the path over time, as orbits have been adjusted and acquisitions have been adjusted, those do shift a little bit, and so that can cause problems. For example, if you're doing an NISAR time series, and you expect that you're going to have data that continues all the way down through your time series, you can see some shifting there. However, working with Sentinel-1 bursts, those bursts are geostationary on the ground. So a burst with a particular burst ID is always going to be in the same location, whereas the scenes that contain those bursts sometimes include different bursts as the frames have shifted. We also provide access to ALS Pulsar, ALS Abnir 2, Circe. We've got the ARIA S1 Gun Ws, which were originally designed to be in the NISAR format. We have heard that there may have been some changes since these were first produced. So I don't think that we can currently guarantee that these are going to be formatted exactly as NISAR products will be, but they were at one point several months ago, and they're pretty close. We've also got SMAP and then UAVSAR. So UAVSAR can also be useful in the context of preparing for NISAR, because these data are acquired in, there's an L-band sensor. In terms of the onboard L-band sensor on NISAR, these data look very similar to the NISAR data. They are not formatted in the way that NISAR data will be formatted, but they've been downsampled to look very much like NISAR data, to provide scientists with the ability to start looking at working with data that is similar to data they might see coming from NISAR. We've also got RadarSat, ERS, JERS-1, AirSAR, and CSAT. So I'll for the purposes of this workshop, I'll stick to Sentinel-1 here, and then there are a number of different ways to search that data set. And so there's a geographic search, and so you can use a geographic search in a couple of different ways. If you have an area of interest in the form of well-known text, you can just paste that in here. You can also draw a bounding box on the map here, and so you can zoom in with your mouse wheel and pan around and select different areas of the globe that you're interested in, and then simply click your mouse button and just start drawing a bounding box. And then if you want to create a bounding box somewhere else, you can just drop another one. If for some reason you've navigated away from the website and you come back and you're having trouble drawing a new bounding box, you can, there are a couple of ways to get around that. You can either clear your search here, or you can come down to this little toolbar and click on this icon here, and just select draw a box, and then that will give you back your bounding box drawing capability. You'll notice that there are also options to draw different features for intersecting with data. So you can just place a single point. When you create any kind of area of interest, be it a point, a line, a polygon, or a box, or a circle, when you search the data on Vertex, it's going to provide you with with anything in your search parameters that intersects with that area of interest. So you'll see scenes that extend past that boundary as well. Now that I've I've created an area of interest here, I could just search the entire archive for everything that touched that, everything in the S1 archive, in the Sentinel-1 archive that touched that bounding box. But you can also refine those search parameters. So right here, you can enter a date range for the data that you're looking for. So you could search just a single year or multiple years. And then if you click this filter button, I did that kind of fast, so I'll just go back. So this little filter button here with the ellipses, this brings up additional filtering options. And so you can select just the SLC. And in this case, I'm going to select the IW beam mode. You can pick a particular polarization or sets of polarizations. You can also select a particular orbit direction. If you don't select either of these, it will just provide you with both both orbit directions, and in this case, all polarizations. And then the Sentinel-1 mission has two satellites currently in space. Although S1B is down, we do also archive all of the historic S1B data, and when S1C comes online, that will also be an option here. And so at this point, I'll just click search, and we can see what pops up. All right, and so it found 250 scenes that intersect this area and match the parameters that I provided in the filters. And so let's say I was looking at this, but I was only interested in scenes falling along this particular path, and the rest was just sort of cluttering up the screen. So I could select one of the scenes in this path, and then look at the scene detail in the middle pane right here. And I can get some information about that scene, such as its beam mode. It's on path 34. This is frame 502, and this is in the descending flight direction. And so if I wanted to limit what was showing on my screen, sometimes when you do a search, you end up with so much clutter that it's hard to actually select the scenes that you're interested in. Or if you just want to narrow down the returns in your search results here, so that you can then either add all of those to your download queue in bulk or order on-demand processing in bulk, you may wish to reduce the results. So with that in mind, I'm just going to I'm going to look at all of the scenes that were in path 34 and frame 502 and eliminate all the rest from this particular search. So I'll go back to my search options, my search filters, and I'll put in path 34 and frame 502. And then refine the search. And now we only see the scenes that fall on path 34 and frame 502. And so you can see there are now 28 scenes that we acquired over the course of 2018 in this area. And so at this point, I could add individual SLCs to my download queue. And so when I click this little shopping cart button, you can see that one new scene has been added to my download queue here, to my shopping cart. However, if I wish to download the entire this entire set of SLCs, I could add all 28 files to my downloads with the Q button up above the search results. So now I've got all 28 of those. And once they're in the queue, I can download those files individually with this little download link here. But you can also download the entire set of SLCs with the download all button. Or if you wish to incorporate this into a programmatic workflow, you can access a Python script that will also download all of these SLCs with this download Python script button here. And so that's if you were interested in the SLCs, but if you wanted to order some RTCs from from this stack of SLCs, once again, you could do that. You could order those RTCs singly by clicking the HyP button next to the scene in the search results, and then selecting a processing option. And so this is the button that allows us to interface with ASF's on-demand processor called HyP. And so HyP allows for currently provides access to 3 different processing options: radiometrically terrain corrected products produced with Gamma software, interferograms also produced with Gamma software, and auto-riff products, which provide velocity maps and are useful for tracking ice movement. So in this case, if I wanted to order one RTC Gamma from this SLC, I would just click to add one SLC job, and now we can look in our on-demand queue and see that this job has been added. However, if we wanted to add all of those, similarly to how we added the entire bulk batch to our shopping cart, we can order on-demand processing for all of these 28 SLC jobs as well. And so now I have 28 jobs in my on-demand queue. And you'll notice that there are a number of processing options and ways in which you can filters that you can apply to the processing, and additional data products that you can request to be included with your output RTCs in this case. So you can select either gamma naught or sigma naught. You can have it in power, decibel, or amplitude scale. You have multiple resolutions that you can select from, so it defaults to 30 meters. Keep in mind that if you select a 10 meter, your data are going to be much, much larger. We have sort of found a sweet spot between having improved resolution and still keeping a much more reasonable sized output product with the 20 meters. So that's definitely worth exploring. And we, up until I think about a year and a half ago, we did all of our radiometric terrain correction with the SRTM DEM, which is still available as an option, but we now default to the Copernicus DEM. Then you can include speckle filtering, or DEM matching. You can include that DEM and the incidence angle maps and the scattering area map and an RGB decomposition image with these products or not, just depending on whether you select them or not here. And then once you have all of your all of your parameters in place, you can select or click the Submit Jobs button. Before I click that button, I just want to point out that there's this little notification to the left of the button that says 1,000 jobs left this month. And so every HyP account has a monthly quota of 1,000 jobs. So you can only submit up to 1,000 jobs per month. There are, on occasion, instances where you may need some more, and if that is the case, please reach out to us. It's sometimes possible to give you a one-time bump in the amount of jobs that you can process, but it's not our standing operating procedure. It's sort of for special cases. So please reach out if that is a requirement of yours, and we'll see what we can do. But there are no guarantees there. And once you've ordered these jobs, they and those data are processed. Those are stored for 2 weeks, and you have access to those data for 2 weeks. So I'll go ahead and submit these 28 jobs, and I highly recommend providing a project name, because if you don't provide a project name, it will still run and process those jobs, but they will become more difficult to identify and download later. It's nice to have that project name label when you're searching through your HyP jobs. So now I'll go ahead and I'll submit those 28 jobs, and we should see that, yes, a little pop-up here says 28 jobs have been submitted. And then if you hop over to the on-demand products here, to the on-demand product search type, then you'll see all of your on-demand jobs, current and historic. And so not only will you see the jobs that you've just submitted, you'll see any that were previously available and any that were that have expired and are no longer available. Oh, looks like we're having a little bit of trouble on the site. Let me just try this again. Okay, here we go. Okay, so I've just submitted those 28 jobs, and now you can see that they're all here with the status of pending. And if I scroll down, oh, seems like something is frozen. Oh, there we go. I was just being impatient. Okay, and so now if I scroll down, you'll see that I also have expired jobs, and if your jobs have expired, you can always reorder them. Once again, you can do that. Having a little bit of a delay on the website here, so it's not responding to my page unresponsive. Wait. Okay. Well, I'm having a little bit of trouble here on the site, but if I clicked this expired button, there we go. Okay, I could resubmit this job, this single job, or I could resubmit the entire project. So don't worry if your products expire, you can always reorder them easily enough by coming to the on-demand search type here in Vertex. There are also some other ways that you can search data on Vertex. I'm just going to try refreshing my screen here, I think. Or maybe just starting a new search. Okay, well, unfortunately, it appears that we're having some slight issues on the website at the moment. But luckily, I started with the most important the most important search examples for this workshop. Let's see if it cooperates. I will also show you a couple others here. Okay, yes. So if you happen to have a list of scene IDs that you'd like to search, as opposed to it, knowing the geographic area that you're interested in. Then you can just paste those into a list search here, and discover those, and either download those SLCs or in this case a GRDH, or order on-demand processing off of those data. If you, let's see, let me go back to the geographic search. We also provide tools for ordering interferograms. I'm not going to go very in depth into the use of those tools. That takes a bit of time, and we're almost out of time, I think, here for this particular session. So I'm not going to go into those details. But if you review the recordings of the previous workshop, we do go into much more detail in how to use the SBAS tool and the baseline tool to build interferograms and stacks of interferograms. And so let's see if I just filter this for some SLCs. Okay. And that is not an SLC. Oh, it's because I don't have a good search area in here. I need to add a box somewhere. Okay, and so now if here I have an SLC, and if I were interested in creating an interferogram off of this SLC, using this SLC as a reference, and I just wanted to make a single interferogram and see all of the potential options that I have for making that interferogram, I would use a baseline search. So you can either go directly to a baseline search here if you know the scene ID already, but if you search for the scene ID using something like a geographic search and select it here in the search results, you can also just click the baseline button here in the scene detail, and that will direct you right into a baseline search with that scene. And when this pops up, it will show us all of the potential secondary scenes that I could match with this reference scene to produce an interferogram. Okay, yeah, and so here are all of my options for creating interferograms, and so I could order all of those interferograms once again here in with the bulk on-demand ordering tool. I could add all of those, or I could order just the specific ones I was interested in. Another option, if you're not just looking to make individual interferograms, but you're looking for connected stacks of interferograms for a small baseline time series, you can click the SBAS button, which was, I guess I did that kind of quickly. It was right along in that scene detail, right alongside the baseline search button. And this will do something similar, but instead of just identifying all of the potential individual interferograms, it creates complete networks of interferogram stacks. And so in here you can adjust the temporal and perpendicular baselines to play around with the size of the stack, and there are filters. Once again, I'm not going to go into a lot of detail here, but you could adjust the date range, and you can apply seasonal searches and add thresholds for mandating some type of overlap requirement. And then we've also got an event search here, which contains a number of RTC and NISAR data sets over areas around the globe that have experienced either volcanic or earthquake events. And so this does not contain, every earthquake and volcanic event that happens, but so these are manually added based on interest in the community. So if a large event has happened with a great deal of interest, we'll typically add that to the event search, and you can search those here and just click around on different events and access analysis ready NISAR and RTC data without having to order it necessarily through HyP. Those have already been produced. And then we have some additional derived data sets. And once again, these are data sets that are ready to download. These don't require additional processing. You can just select any of these and find yourself directed to a website that will enable the downloading of those data. All right, and then the last slide in this little section on Vertex here is I think we showed these earlier, but we have these beautiful story maps that Heidi put together that walk you through a lot of what I just showed you plus more. So they will guide you through the steps of ordering RTCs and interferograms. And there are a number of interesting story maps covering additional topics as well. So I recommend just going to this site and browsing those story maps and exploring those. Those are great resources. All right, welcome back, everybody. I'll just share my screen again and proceed with the next section. Okay, so now I'm going to cover an introduction to RTC, radiometrically terrain corrected processing, and using HyP. So I just described how to order RTCs with HyP in Vertex, but then there's also a HyP SDK and API, so you can also access those data programmatically, or that on-demand processing programmatically. And so I'll cover a little introduction to that as well. But to begin, I'll first give a description of radiometric terrain correction. So as Heidi mentioned earlier, radiometric terrain correction corrects for both geometric and radiometric distortions. And this is important because those data are sort of warped out of shape and have inaccurate pixel brightness associated with the backscatter due to the radiometric distortions. We perform this correction to accurately sort of warp that image back into shape to put the mountaintops where they belong, so that when you drop it into GIS software, everything aligns, and when you analyze them alongside other data sets that do not contain those distortions, that everything is co-registered and neatly aligned, and that the brightness for those distorted pixels, once they've been corrected for the geometric distortions, those brightnesses, the brightness in those pixels are also corrected to accurately reflect what is on the ground, and not the fact that a whole bunch of returns have been kind of crammed into a few pixels. So in SAR, there are several different geometric distortions that can occur, and this is this is an artifact of the fact that we are using a side-looking radar, and we have to use a side-looking radar because if we used a nadir-facing radar, if it pointed directly straight down at the planet from the sensor, then we would end up with a footprint on the ground that was directly underneath the sensor and had symmetry on either side of the sensor. So a point that returned from here would be indistinguishable from a point that returned from the symmetrically located spot on the other side of the sensor. Because these returns are ordered based on the time that it takes to send the signal and then receive it, the time that it takes to bounce and hit here and bounce back would be the same as if it hit in a matching location on the other side. And so with a side-looking view, our near range is going to always return sooner than our far range, and we can then distinguish the location of every point in range in the footprint of our signal. And so there are three types of geometric distortions that occur because of this side-looking view, and those are foreshortening, layover, and shadow. So foreshortening occurs when, its effects decrease with an increased look angle, and it occurs on the sensor-facing slope. So if you picture in this figure here to the left, if you picture that there is a sensor, up in space somewhere around here, then this red slope here of this imaginary mountain, this red slope is the sensor-facing slope, and the blue slope is facing away from the sensor, and then this plane here is the image plane, and so when the ground range are projected into the image plane, this is where we see these geometric distortions. So you'll notice that while our mountain looks pretty symmetrical and the length of the red sensor-facing slope is pretty equal in length to the blue slope facing away from the sensor, when these are projected into our image plane, because of this side-looking view, all of the returns from the sensor-facing slope are crammed into a much smaller area here. So the points between A and B end up between A prime and B prime here in the image plane, and so all of the not only does that then appear smaller, but it also all of the amplitude returns from all of these locations are sort of crammed into a fewer number of pixels, thereby creating the radiometric distortion where these appear brighter. So if you look at this example on the right, you can see that there is a mountain here, and there's this very thin white edge, very bright edge here, and you can see a little bit of this face, but it is much smaller than the back face facing away from the sensor. And so in reality, it's likely that that this is not a very small slope, but it's probably a fairly symmetrical mountain, and but we're just creating distortions due to the side-looking view of the radar. And so you can also see that, of course, in the other mountains here, these long, darker back slopes, and then these very narrow, bright foreslopes. Another type of distortion is layover, and it happens for much the same reason as foreshortening. But in this case, it leads to an effect in which tall objects, mountains, and tall buildings appear to be laying over on the ground in front of them. And so if you look at this figure on the left here, you'll see that the returns from the top of the mountain, the entire sensor facing slope, end up once again in this smaller, too small of an area in our image plane. But the ground in front of it also ends up in that same area. So this green area on the ground in front of the mountain also ends up projected into the same area as the foreslope, and a small portion of the back slope of the mountain also is projected into that same area. And so you have all of the returns from these three different areas sort of crammed into this one small region of the image plane, whereas the remaining part of the back slope ends up in a much larger area here. And so this is why these why the mountains appear to be laying flat, because they've really been combined with the returns from the ground in front of them, and even a small portion potentially of the back slope. And so looking at the image on the right here, you can see that there are two mountain ranges, and this is actually a valley between the mountain ranges. And in reality, this mountain is not laying inside the valley. We should be able to see down into that valley, but due to the geometric distortions of layover, these mountains appear to be laying on their side. And so the effects of layover also decrease with an increasing look angle. Then the third type of geometric distortion is shadow. And so there are instances where there are portions of the terrain that are completely hidden from view and never receive a signal from the sensor, from the transmitting sensor, because well, frankly, the mountain is in the way. And so you end up with these completely black areas where there is no return from the ground, because it was never illuminated with the transmitted signal to start with. And so those geometric distortions lead to radiometric distortions, because we have condensed, large areas into a smaller number of pixels, and along with just those pixels being condensed, we've also accumulated all of the returns, all of the backscatter returns from those areas into those smaller areas. We end up with often drastically increased amplitude in those areas. And so, once again, foreshortening creates this sort of thin white line along the foreslope of a tall mountain, and then layover makes it appear that, in this case, this volcano makes it appear that the volcano is kind of laying over on the ground in front of it, and those effects combine to over brighten these pixels along this leading edge here of the mountain, the foreslope that's been sort of all crammed into one location. And so it's not simply enough to rewarp the image and remove those distortions while not addressing the radiometric distortions, because then we'll end up with seeing a nice a more accurate depiction of the mountain with the full slope in view, but they would remain overly bright. And so we also have to account for that over brightness and normalize that brightness based on the actual area contributing to the backscatter returns. And so I'm going to go through the steps with which a radiometric terrain correction is performed. But before I do that, I really want to point out that this is not something that you should ever have to do in all likelihood, especially for Sentinel-1 and NISAR data. There are sources for you to order or retrieve those RTCs without processing them yourself, unless you have some special parameters that you're looking to incorporate into your own radiometric terrain correction. You can just order these products from HyP on demand, as I demonstrated in Vertex, or soon you'll be able to get pre-processed RTCs from the Opera project, which is coming, which will be releasing the RTC data set within the next several months, and then NISAR is launching next year, of course, and NISAR will have RTCs as a standard product. So the basic steps of RTC are co-registration with a DEM-derived simulated SAR image. So this is just a DEM that has been projected into slant range geometry to match the SAR image, and then the geometric distortion, and then the radiometric distortion correction. And so I'm going to walk through those steps, and the information that I'm about to present was all taken directly from the ASF radiometric terrain corrected products algorithm theoretical basis document, which is linked here. So you can find this, and in fact, I'll just hop over and show you that really quickly. Except this is in the way. Okay, so you can find more detail than I'm about to provide you with in this ATBD, which is linked in the slideshow here. All right, so co-registration. So we begin by co-registering the SAR image with the derived with the simulated image derived from the DEM, and so both of those images are tiled, and initially this is the sort of the flow chart of how this works. So initially a single match is attempted between those tiles, and if the signal to noise ratio, if the threshold of 10 is not met, then or if the signal to noise ratio is lower than 10 rather, then gamma matches, then starts doing the initial tile matching on a coarse grid. I believe that the gamma implementation actually does do, even if that threshold is met, it does do one further sort of subgridding into a finer grid, but additional layers of regridding into a smaller grid is performed if that signal to noise ratio is too high, if it's over 10, and then once you get down to a fine grid, then any points that have a signal to noise ratio greater than 10 are removed, and at that point, each of the corresponding small tiles, are matched, and if there's an offset within 50 meters or two standard deviations, then an offset model is applied. However, if the offsets are too large, then dead reckoning is used, and so that uses the orbit data to do that co-registration. Then for the geometric distortion correction, range pixel sizes are converted from slant range to ground range using the center ellipsoidal incidence angle, which is included in the metadata of the SAR image. And then the corrected number of azimuth looks are calculated, and this is done as the ratio of ground range projected pixel sizes in azimuth and range direction. And it also takes into account the posting size, so the resolution often in our cases 10, 20, or 30 meters, although that could be anything. Just when you're ordering from HyP, the options are 10, 20, or 30 meters. And so at this point, the image has been sort of warped back into shape, and the artifacts of those distortions have been removed. However, the brightness, the amplitude is not accurate because, as I described earlier, areas where all of the signal were accumulated into a smaller area, while we've stretched those out, we haven't done anything with the brightness yet. And so the next step is radiometric distortion correction. And so that normalization is done using a pixel area integration approach. And so to do that, the DEM is divided into rectangular regions, and then those are subdivided into triangular facets. And then the surface normal is defined for each facet. And at least for gamma software, where a facet does not lay within a single range sample, they're further divided into additional rectangles and additional facets. So a finer resolution of facets. Oops. And then based on the geometry of those facets, surface normals relative to the radar look vector, the projected pixels areas are calculated and added to a pixel area map in range Doppler coordinates. And then once we have that pixel area map, then the radar brightness is adjusted by multiplying that brightness by the ratio of pixel area from the ellipsoidal reference over the integrated pixel area. And so these are just a few figures taken from that algorithm theoretical basis document. So this kind of walks through the steps that I just described, this flow chart here. And then this is just an illustration of binning those up into our rectangular tiles, and then creating those facets from which the surface normals are taken, and then it's projected into the slant range here. And so, as we've said, you can order these RTCs from HyP in Vertex, as I showed. There are links here to the RTC product guide, and once again to the RTC on-demand story map. And then there are a couple links to notebooks that show you how to access HyP programmatically to order and download your data from a Python workflow. And so I will quickly just demonstrate one of those notebooks. So I pulled one of those notebooks here into OpenSAR Lab. And so if you're not familiar with it, OpenSAR Lab is our Jupyter hub that we'll be using tomorrow during the running of the notebooks. And so this particular tutorial can be found in the, it's linked in the slideshow, and it's found in the HyP documentation. And so the first cell here is just going to install ASF search in the HyP SDK if you don't already have them installed. And then you'll notice here that we are defining some search parameters and job specifications. And so much the same way that you could edit in Vertex, you could edit those filter options to include different date ranges and define an area of interest and determine processing levels and orbit directions, and all of those options are available as well through the SDK. And so you can define your search parameters in a dictionary such as this. And then when it came time to order those data from HyP in Vertex, you may remember that there were additional products that you could request, and you could set the resolution, and you could and the job type, and you could define a project name, and so that you can also do that here in the code as well. And so I'll run that. And I did make one small edit to this notebook after downloading it, and so I'll show you that, because so you're not surprised if you download this notebook yourself. So I believe this notebook does not include the prompt equals true, and so if you run this in an account and it as it's coded here, it expects you to have your Earth data credentials in a .NET-RC file. And so if you don't, you'll get an error like this. It will say, was not able to authenticate with a .NET-RC file, no credentials provided. And so if you can either set up a .NET-RC file, another option is to simply add the argument prompt equals true. And then when you run this code cell, it will prompt you for your Earth data credentials. And you can enter those in here. Password in the okay. And so you'll see that it has successfully logged me in, and then it searched based on these on these search parameters. It searched for previously processed granules, and it didn't find any. But then it also searched for the availability of granules that we could process, and it found 104. So I'm not actually going to run this next step, because I don't want to kick off that job with 104 granules. But all I would need to do to order those data would be to run this code cell here, and it would order all 104 of those RTCs. You can see here in this line of code, it would submit prepared jobs, and then it would take. I don't think I mentioned during the Vertex, it takes about an hour, regardless of how many products you order. It tends to take about an hour to do that processing. So it's a high throughput service. So HyP will spin up as many machines in AWS as it needs to process all of your data at the same time, and then deliver all of those at the same time. It doesn't go through each one sequentially. And so that's just a quick little demonstration of how you can work with HyP programmatically. And once again, you can find the notebook that I just ran through, and additional notebooks and additional material describing how to use the HyP SDK in the HyP docs, which are all linked here. And so that concludes the main part of our workshop today. The last section we've reserved to help everybody get set up with Open Science Lab and Open SAR Lab accounts if you need, and make sure that you have you've been able to clone in those repositories and the repository you need, and build the content environment that you need, and also set up your Earth data logging credentials if you don't have them for access to ASF data. Although that last step, setting up your Earth data credentials so that you can order data from ASF and HyP, is not required for this workshop. It will be of great benefit to you if you wish to order your own data in the future, to go through a similar workflow. So at this point, can people well, so we did send out that preparatory slideshow, and so it's possible that everybody has already completed all the steps and has everything that they need. But can anybody who still needs either an OpenSAR Lab account or help pulling in the repo or building the content environment, can you please just make a comment in the chat so we can get a sense of how many people and if anybody needs help with these steps. All right, I'm not seeing anybody respond. So maybe what I'll do is I will just walk through how you would do this, just in case. But if anybody has any specific questions on the process, please just put those questions into chat or the QA. So to set up or to create a new Open Science Lab account. Oh, I'm not sharing. Let me just share my screen again. Okay. To set up a new Open Science Lab account, I'm already logged in, so I'm just going to open a incognito window here. Just head to Open Science Lab.
Hey, Alex, we're still seeing your slides.
Oh, okay. Thank you for that. Let me just share the whole screen. Okay, I think I'm sharing the whole screen now, not just the slides.
Yep, we can see the incognito window now.
Okay, great. Okay. So I'm just going to head over to opensciencelab.asf.alaska.edu. And when you get here, you'll notice a little pop-up that just lets you know that that temporarily we have turned off automated authorization of accounts. So an admin will have to authorize your account. So if you have completed the sign-up process but are not yet authorized, please put that in chat. And Dylan Palmieri is on the line with us, and he will hop on and authorize you as you put your usernames into chat. But if you have not yet signed up for an Open Science Lab account, you can just click the sign up button here and complete this short form, agree to the terms of service, and click the create user button. At that point, you'll have to open your the email that you provided and click an email confirmation link in order to confirm your email with the system. And at that point, we'll be able to authorize your account. So that is how you sign up. Just shut down the incognito window now. And okay, and so now over in OpenSAR Lab, once you've gained access to OpenSAR Lab, and you actually, I should probably just log out here to show you what it looks like when you sign in. Okay, so when you sign into Open Science Lab, you'll see that you have the option to go to the OpenSAR lab. So click that Go to Lab button, and then click the Start My Server button. And then you'll have a number of server options. You may not have every single option that you see here. I think I probably have a couple of extras turned on for myself. But you should see the SAR1 and the M6A X large and the M6A large. And so the SAR1 is a shared profile. So it puts multiple users onto the same EC2 instance in AWS. And while generally this works very well for our users, we have run into some issues in workshops like this where everybody is going through the same operations at the same time. Sometimes those shared instances their memory can be overrun and people end up getting evicted. So for the purposes of this workshop, I recommend using the M6A large. We've tested this, and the M6A large is large enough to support the building the environment and the notebooks that will be running. And this is a single user instance, so there will never be any sort of conflict between users competing for resources on that machine. So I'll select the M6A large single user and start my server. And hopefully this won't take too long because I was just in one, so it should still be up and running. Hopefully it hasn't shut down yet. If it has, it may take a couple minutes for this to load. Well, it looks like it did trigger scale up. So I think it is going to require starting a new machine. So this will just take a minute or two. Okay, and while this is thinking, I'm just going to hop over to the repo that we're going to want to clone. And so this is in that data prep notebook. And it's in the ASF HyP. Oops, that is the docs. It's in the ASF HyP GitHub org, and it is the tutorials repo. And you shouldn't have to find it the way I did just by searching Google. That link is in that data prep, or sorry, that workshop prep slideshow. So I'm just going to do an HTTPS clone of this into my my OpenSAR Lab account once it loads. So while these single user instances, reduce the chances or eliminate the chances that users will conflict with each other when performing the same operations at the same time, they do take a little bit longer to load because they're not a shared instance. We don't have sort of pre-warmed instances on hand to just hop into. So it does take a little bit of time to spin up that machine and get going. Okay, and so now we're back in OpenSAR Lab. And so I've already cloned this repository, so I'm just going to go ahead and delete it so I can show you. Oops. Okay, so I've removed that tutorials repo. So when you find yourself in OpenSAR Lab, you'll see a screen something like this. You won't probably yet have this ASF IGARS 2023 tutorial content environment displaying. So you'll probably just have these base environment notebook kernels and console buttons here. And so the first step is going to be to download that repository. And so you want to click a terminal button. And if you happen to have a notebook or something up on screen, you can always get a new launcher by clicking on the blue plus button here. And so that just opens up a new launcher in a new launcher tab. So then click the terminal button, and then you'll end up in a terminal. And then you can just do git clone and paste in that GitHub link to the repo. And so now you can see, once again, I have my tutorials repository here, and here is the IGARS 2023. And this is the environment YAML for the environment that we are going to build for using with the IGARS landslide heat maps notebook, which is the notebook that Forrest and Jackie are going to be showing you tomorrow. And so if I open up this YAML, you can see that it will create a conda environment called ASF IGARS 2023 tutorial. It's going to install all of these conda packages from the Conda Forge channel of Anaconda. And these are the packages that it will install. A couple of them are pinned to specific versions. And then it also performs one pip installation of a package called DemStitcher. So to install this environment, you just go to the home directory. You can always get back to the home directory in your file browser in Jupyter here by clicking on the little folder button on the far left at the top here. So if you're buried deep in some in some nested directories, you can always get back by just clicking that little folder button there, and that will bring you back to your home directory, where once again we see our tutorials directory, but there's also this conda environments directory here. And so if you open that, you'll see a notebook inside called Create OSL Conda Environments. And so I'm going to open that. This is showing output from a previous run. So I'm going to clear this notebook, which you can do by selecting the kernel menu and then restart kernel and clear all outputs. And then click restart. And so now we have a fresh kernel, and all of our old output has been removed. And then we can start stepping through this notebook. And if you're not familiar with notebooks, there are a couple of ways that you can run the code cells in notebooks. You can click the little play button up at the top here. And while it's processing, you'll notice that there's an asterisk in these brackets. But then once the cell has completed processing, it will fill those brackets with a number indicating the order in which the code cells were run, which is important for notebooks because notebooks allow you to run code cells out of sequence. So this is a handy tool to let you know where you're at in the notebook, in what order you've run your code cells in. Another way to run the code cells is with a shortcut which is Shift Enter. So if you hold the Shift and hit the Enter key, it does the same thing as clicking the little play button there. And so this cell just prints all of your available conda environments. And since I've already built the environment, I already have the ASF IGARS 2023 tutorial. Unless you've already built this, you won't see this when you run that code cell. This cell just directs you to a minimal example of a notebook or of a YAML. So if you wanted to create your own environment and build it using this notebook so that it works with other notebooks in OpenSAR Lab, you can get an example of the minimum requirements for putting together your own YAML. And then this cell prompts you to select whether or not you'd like to build one of the built-in OpenSAR Lab ASF provided environments, or whether you would like to point it to YAML, an environment YAML that's located somewhere else. So if I ran it with the ASF environment, to use an ASF environment YAML, you would see a list of all of the available environments that we've provided. And so those YAMLs are in this environment configs directory right here. Yeah, so these options correspond to these YAMLs here. But that's not what we're doing. Today, we are going to build a YAML from the repo that we just cloned. So I'm going to select use another YAML and then rerun this code cell. And now instead of providing me with that list of pre-baked in options, it gives me a file chooser. And so now I can go and locate the environment YAML that's in the repo that we cloned. And so this opens up to the current directory. And so we need to back out to the previous directory. And to do that, you just click the directory icon here with two periods. And so that will back you out. And now we can see the tutorials directory here. So I'll click on that and then click on IGARS 2023 and then select the environment YAML and then click the select button. And then I'll run the next couple code cells. And so this code cell outputs the location where it's going to save this environment. And you'll notice that it's in the .local directory. And that's important because that is on your OpenSAR Lab user's volume. So that's a persistent volume that will remain as you left it. So the next time you come back, you won't have to rebuild that environment. If we had saved it to the default Conda location, it wouldn't even have the permissions to do it. But if it did, it would try to save it to into the Docker container, and that would all be lost when you shut down your server, and then you would have to reinstall the environment every time you came into OpenSAR Lab. So this is saving it into the .local directory of your user volume, which persists across server restarts. And so then finally we get down to this code cell, and this is the cell that will actually build the Conda environment. And so in my case, I've already built this environment, but this does a force overwrite of that environment. So it should still rebuild that environment. And this will take several minutes to run. I don't think that we have to necessarily sit and wait for this to run. The main point is if you've gotten to this step and run this cell, then you should be all prepared. And in that preparatory slideshow, I did provide a screenshot of the output that this code cell displays once it has completed creating that environment. And that should put you in, once you've completed all of those steps, that should put you in a good place for picking up with tomorrow's workshop and walking through the notebook alongside Forrest as he presents it. And so with that, I think we can conclude today's workshop. Does anybody have any final questions before we wrap things up? Or do any of the other presenters have anything they'd like to say before we go? So, Dr. Rao, I just saw your question. So HyP on-demand processing uses Gamma software to produce those RTCs. So yes.
Yeah, we might change a few settings from what the Gamma defaults are, but if you go into the HyP Gamma repository on GitHub, you can see what settings we've changed.
And with that, thank you all so much for staying late in your day and attending the first day of our workshop.